In July 2025, an advanced version of Gemini achieved gold medal standard at the International Mathematical Olympiad. The model solved 5 complex problems perfectly, branching through thousands of possible reasoning paths before outputting a final answer in natural language. This milestone is the result of a 15-year engineering pipeline. Since its inception, Google Deepmind has worked to remove human data as a bottleneck, replacing manual heuristics with systems that can verify their own progress. This matrix identifies the 3 architectural pillars that made this breakthrough possible. It traces the evolution of reinforcement learning in games, the development of generative physical simulators, and the eventual scaling of formal logic. Google Deepmind's research strategy relies on a specific sequence, establishing fixed mathematical boundaries, bypassing human data through self-play, and scaling compute during the thinking or deliberation phase of a query. Early reinforcement learning was bounded by human capability. The original AlphaGo system, which defeated Lis et al. In 2016, required initialization on 30 million human expert moves before it could begin to learn for itself. AlphaGo Zero removed that requirement. By operating within the fixed rules of a Go board, the agent learned entirely through self-play, eventually defeating the version that beat Lis et al. By a score of 100 to 0. Deepmind later applied this same search framework to fundamental mathematics. By framing matrix multiplication as a game, an agent selects actions to decompose a complex tensor into smaller, more efficient vector representations. This led to Alpha Tensor, which discovered a way to multiply 4x4 matrices using exactly 47 scalar multiplications. It surpassed a computational limit that had stood since 1969. AlphaDev applied this game-theoretic model to assembly code. By evaluating the latency of CPU registers, the system searched for faster ways to execute basic operations, discovering branch list instruction sequences that improved C++ sorting speeds by up to 70. It can generate a 10-day global forecast in under 60 seconds, a process that previously required hours of supercomputer time. This localized approach was also applied to biology. While AlphaFold 2 successfully predicted 200 million protein structures, its accuracy was often tied to the availability of deep evolutionary sequence data. AlphaFold 3 moved toward a generative architecture. It uses a conditional diffusion module that operates in real coordinate space, iteratively denoising a cloud of points to build stable 3D atomic structures. By utilizing atom-by-atom tokenization, the model can now account for non-protein entities. This enables the precise modeling of how proteins interact with DNA, RNA, and small molecule drugs. By replacing traditional physical simulations with localized neural networks, Deepmind shifted its focus from calculating physical reality to generating it. The final hurdle for these models is rigorous logic. Large language models often fail at complex mathematics because they are prone to hallucinations during long, multi-step deductions. Alpha geometry solved this for Euclidean plane geometry using a hybrid system. A language model proposes a geometric construction, such as a new line or midpoint, which is then verified by a formal deduction engine based on absolute logic. AlphaProof expanded this search capability. It uses a Gemini model to translate natural language into formal code for the lean theorem prover, using branching nodes to isolate easy and hard subproofs in parallel. In July 2025, Gemini DeepThink removed the need for this translation. The model now operates end-to-end in natural language, generating rigorous mathematical proofs directly from official problem descriptions. This relies on parallel thinking. During the deliberation phase, the model explores multiple solution paths simultaneously, terminating branches that fail internal checks while expanding those that show mathematical promise. This demonstrates that solving advanced logic does not require a specialized formal language. It requires scaling the compute available to the model while it evaluates a problem. When we look at the evolution of search mechanics across these architectures, a single engineering through line emerges. Deepmind is building algorithms that establish their own training targets and verify their own results. This removes the need for human data labelers or hand-engineered rules. This framework is already identifying stable inorganic crystals, accelerating the discovery of new materials, and resolving long-standing problems in algebraic geometry. We are seeing these specialized research tracks consolidate. The same reasoning loops used for games and proteins are now being integrated into omnimodal architectures capable of native logic and code reasoning. By engineering systems that can autonomously verify their own logic, Google Deepmind has created a functional blueprint for the future of scientific discovery.